Y'all are busy, I am busy, so today in one video we're going to cover chapter 2, 3, and 4, and in the meantime I'm going to show you guys how I study for exams like these and how I remember this type of stuff. Let's start off with chapter 2. Chapter 2 is motion in 1D. I'm going to literally spit off all the equations I remember from this chapter. You guys should try to get to the same stage. You don't have to remember the equations, but if you see the equation and you know what it is, that means you've been through several problems so that this equation is now becoming a little bit more familiar than just never seeing it before. If you guys are at the same stage, you should feel a little bit better about the exam. If you're not, just keep studying, keep writing down the equations, and check out this video over here where I teach you guys how to remember shit like this, which is important. So, equation number 1. Average velocity is equal to displacement in position over displacement in time. Displacement in position is equal to final position minus initial position. If I use this equation and I multiply both sides by delta t, I can have V average times t is equal to delta x. And then if I use this equation to manipulate this equation a little bit more, I can replace the delta x with xf minus xi. I have here xf minus xi. I just flipped the equation, so the left-hand side goes on the right, and the right-hand side goes on the left. And then I can just isolate for final position as a function of time, and this is equal to average velocity times time plus initial position. So this is a identical form to this, y equals mx plus b. And from this you can kind of approximate what the position time plot of a particle will look like if it has constant average velocity of v. It will look like this. Here is the y-intercept, the b. I'm going to circle this in pink. This value here is initial. If we go a specific length in time, let's say t is equal to 15.7 seconds, then we can go upwards at this unit in time, 15.7 seconds, and find where our graph hits this. And this value is going to be x final. And this slope over here, the slope is equal to v average. So this is very important. First equation, or I guess first 3 equations, this one for average velocity, this one for displacement, and then this one over here, which is the main important equation. It is position as function of time for particle under constant velocity. The velocity here is constant and it's not changing, so a particle under constant velocity over time is going to have a position time plot that looks like a straight line. So this is what it looks like in math. This is what it looks like in a graph. Awesome. The next thing you learn in chapter 2 is particles under constant acceleration. So they tell you that acceleration average is equal to delta v over delta t. So now it's the change in time of velocity. The rate of change of velocity. How much your velocity increases over time. Notice the similarities with average velocity. Right? We get a similar equation. Final velocity is equal to, actually, we can put final velocity as a function of time is equal to average acceleration times time plus initial velocity. This is analogous to the final position as a function of time equation, which depended on average velocity times time plus initial position. In here, though, we can have another application of this equation, and that will look like this. Final position as a function of time for a particle under constant acceleration Okay, I actually split it up here. I think it's going to be valuable. We have initial position plus the constant velocity portion of this plus 1/2 AT squared. This is an important equation. At this point, my knowledge of the equations kind of goes out the gutter. I know that we have 2 more equations, or maybe even 3 more equations similar to this one that are valuable for particle under constant acceleration, except I don't know them. So I'm going to go check into the book, go to mechanics part 1, go to chapter 2, and you know what, I'm going to skip to chapter 2 summary, because the summary of the chapter at the end just has all the valuable equations most of the time. Sometimes they might skip out on an equation or 2. In this case, it looks like they don't. We got the equations, and one of them is, again, final position. Final position, here we have initial position plus 1/2 Vxi plus Vxf times time. So it looks like this is another equation. This one I have not used before. Maybe it'll be useful. And let's write the other one, and then we'll talk about what are the differences. So here are the important equations. We have one of them over here, which looks very similar to the one for constant velocity over here. So this is an important equation. It's basically saying, okay, if I start with an initial velocity 0 and then I accelerate to a final velocity 100 kilometers per hour over some time, like 0 to 100 in 10 seconds, my average acceleration can be determined in this way. Then we have 2 equations for final position for a particle under constant acceleration. The first one adds the initial position, initial velocity, how long is your particle accelerating for, and also the acceleration it is undergoing. Notice this little extra term here. By the way, if this acceleration is 0, then this equation just goes back to the constant velocity equation. You can see they look the same here. Boom and boom. So if you have 0 acceleration, this term gets removed. If you have a non-zero acceleration, this term changes this constant velocity problem to a constant acceleration problem. Amazing. This one over here doesn't actually need the acceleration, it just needs the initial and final velocities. You can see the initial and final velocities are over here. They're actually related to the acceleration. And this over here is like an average acceleration, I think. Or maybe it's an average velocity. Because here you have the initial velocity plus the final velocity, you divide this by 2. So this looks like average velocity times time. And it actually kind of looks like this equation here. Boom. Right? This is the average velocity. That's what we have here. Except, why do we have a 1/2? I guess that's part of the average velocity. You're multiplying by time over here, multiply by time over here, and then you're adding an xi. Boom. So this equation is very similar to the one that you learned before. And then a final one, you have initial and final velocity squared, you have the acceleration, and you have the displacement. So this is the only equation with no time. Notice this equation has time here, here, here. These equations have position here, here, here. These equations have velocity here, position here, acceleration, and no time. So these 3 equations, basically just look at them and be like, what information does my problem have? What information am I looking for? Which one of these equations has all of that linked together with an equal sign? use one of them, plug it in, and check and see if something happens. Maybe sometimes you're actually going to have to use one, then you realize you're missing something and you need to get it from another, and you realize you're missing something here and you need to get it from another. So you use this kind of stepping stone system. All the equations here should work. And the important thing is that now you're categorizing problems into those of constant velocity and those of constant acceleration. So distinguishing between these equations here and the concepts that you learned in the chapter is very important. That being said, check the chapter and see how they define constant velocity, constant acceleration, and you should be chilling. Let me check the chapter and see if I miss something. We have the difference between velocity and speed, very important. This picture over here I think illustrates the answer to this, but also if you're curious about this, I would say Google search it a little bit, and if you ever have questions you can drop a comment. Don't stress about it. One final thing is the difference between average velocity and or acceleration and instantaneous velocity and acceleration. I think this picture over here does a pretty good job of explaining it. Again, Google search on your own, see what you think, what is confusing to you about this, and let me know in the comments, or just write it down on a piece of paper and then look at it the next day, see if anything has processed. Sometimes you just need a good sleep and you will go through a revolutionary breakthrough. Now that finishes chapter 2, let's go to chapter 3, which is vectors. I'm going to spew out all the things I know about vectors, as with this video over here. So check out this video, it's a little bit older, and it's going to include more information than what I have here right now. I kind of just want to speed through the chapter 3 and then enter a little bit into chapter 4. So a vector is plotted on a two-dimensional xy Cartesian coordinate system using a point x, y. Notice a vector in the book can be a bolded symbol. It could be V, A, B, W, whatever. Sometimes they also put this little vector line on top. A vector is a two-dimensional object or more. It needs to have two pieces of information. In this case, we have two pieces of information. One is the x and the second one is the y. So these things could be called the components of the vector. You could say x over here and then I hat and y j hat. I hat and j hat represent the components of the vector in the x and y directions respectively. What does this mean? Let's draw this vector v, which I will do in blue. Boom. You have the components of the vector over here. So I can take this, draw a dotted line to find what the x component is. And the length of this side of this triangle is just going to be x. Then I can do the same thing over here. And this is going to be y. Boom. We have y over here. Check out, we also have y over here. And we also have x over here. And over here you can make an angle, which is another thing useful for a vector. So I can write this vector v as a magnitude. So the magnitude in this case will be the length of this vector. We can call that v, or sometimes we see this. So this vector can be written as the magnitude of v at some specific angle. And converting between these two, this component form of seeing a vector and this magnitude and angle way of seeing a vector, this is the most important thing in this chapter. You want to figure out what vectors are, which we'll see in chapter 4, and how to work with them. So first they teach you how to work with them in chapter 3. They give you some examples. I would say practice all the examples for every chapter. I don't want to show any of the examples because I'm afraid showing the book is going to get my video removed. So just go in the book. I know you guys got it. Check through each of the chapters and do each of the problems. There's like each of the examples. Do each of the examples. There's probably like 10 examples per chapter. Do one after the other. Do them multiple times until you're able to do it on your own. So basically, we have how you convert between here and here. And the main way, the thing that I remember is trigonometry and Pythagorean's theorem. If you remember SO, KA, TOA, and A squared plus B squared equals C squared, these two things are exactly what you need to convert between this and this. And I'll show you guys very quickly here, and that'll pretty much be the entire value of chapter 3. So what we have from the previous problem is something like this. where we have our angle theta over here and the length of this vector, let's just call it v. I'll put these brackets around it. We want to convert that into this y component and this x component. So how do we do that? Well, I'm going to straight up write out sine, cosine, tangent. This is from SOHCAHTOA. So I'm first just writing the sine, cosine, tangent right here. Sine, cosine, tangent, all of them are trigonometric functions which eat an angle. So here's going to go my angle, which is this part of the triangle. Each of these guys eat an angle. I'm not going to put brackets on all of them. Most of the time it's in degrees, but it could also be in radians. So make sure your calculator is good. Make sure you know how to convert between radians and degrees. On the other side is where the O, A, and OA goes. So O is opposite side of the triangle. This is a fraction. Opposite side of the angle in the triangle is this y. And the adjacent side is this. So A is over here. O is over here, and hypotenuse is always this. So that is always the h. So using that in sine opposite, we have y. Hypotenuse, we have v, the magnitude of v. Then for cosine, we have adjacent x over magnitude of v. And then for tangent, we have opposite over adjacent. So we have y over x. Amazing. And also, Pythagorean's theorem says if we have x squared plus y squared, square root this whole thing, we're going to get the magnitude of the vector. So this is all you have to know to convert between the two. Let's say I have y and x. The vector is given to me in component form. If I use this equation here, which is literally just Pythagorean theorem, I will get the length of the vector, the magnitude of the vector. If I also have the legs, I can use this equation here and find the angle. I take tan inverse of this, and that will give me the angle. Most of the time in radians, make sure to check your calculator. So these two equations convert between the legs or components of the vector into the magnitude and direction. And if you have the magnitude and direction, you can use this equation here. Just take sine of the direction angle and multiply that by this, which is the magnitude. And that is the equation for y. If you want the equation for x, just do cosine of your angle and multiply that by v, the magnitude of v, and you should get your other leg. So make sure you know how to convert between this, because a lot of the time you're going to have an answer to a problem in component form, but the question is going to be telling you, please give me the answer in magnitude and direction, and vice versa. So go through this. Honestly, guys, this is all I have to say about vectors. Let's move on to chapter 4. And I think the best way to illustrate what we have to do in chapter 4, I'm not going to go through everything. I'm going to just show you guys one problem and you will see what's going on. Here's a problem that's going to get us acquainted with chapter 4. It's not everything, because chapter 4 also includes radial or circular motion and tangential, something like this. So this is going to cover most of the projectile problems. We're going to cover the radial or circular motion in another video most likely. Here's the problem. A long jumper leaves the ground at an angle of 20 degrees above the horizontal and at a speed of 11 meters per second. A, how far does he jump? B, what's his max height? So let's set up a coordinate system and figure out how to solve this problem. I'm just going to speak off the dome and share with you guys what I'm thinking about this. So the guy can be modeled as a particle, and the second he leaves the ground, he is going at some velocity like this. And he's going to travel in some parabolic pattern like this. I don't know if this is a perfect parabola, but objects that are thrown up follow a parabola shape. If you're curious about that, Google search why that happens. Try to convince yourself that it's true. And the information they tell us here is, first, the angle, theta, is equal to 20. Is that true? 20 degrees above the x-axis. And also, another piece of information they tell us is the total velocity, which is 11 meters per second. Then they're asking us how far does he jump. So they're asking us to find this distance here. Let's call that x. How far he jumps for part A. And the maximum height can also be easily seen right here. This is h for part B. So how do we solve this? What you need to do is apply one-dimensional motion in each of the perpendicular directions. One-dimensional motion is happening in the x-axis. One-dimensional motion is happening in the y-axis. You combine them together using a vector, and that is how you represent two-dimensional motion in all of these problems. If this sounds confusing, don't stress, we're going to go through it right now. But it is important that you remember the equations from chapter 2 because those obey the motion that these problems obey. So the equations you learned in chapter 2 are going to be applied here, and that is amazing because we already remember the equations. So what I think we can use here is the jumper, the long jumper's x as a function of t and y as a function of t. All right, in the y direction, it is a particle under constant acceleration. Why? Because gravity is always pulling the guy down. So the constant acceleration equation was this. And we know that the initial position was 0 because that's how we set up our problem. He starts right here at 0. The initial velocity, we don't know what it is, but we do know acceleration is 9.81 meters per second squared. So I could fill up this a little bit. We have 0, and then let's do Vxi times t plus 1/2. Here I'm going to do negative 9.81 meters per second squared, t squared. The reason I'm doing negative is because gravity in this scenario is pulling it down. So whatever position you're going to have here, gravity always pulls it down and should reduce the number. So this negative makes sense. If this was a positive, then the final position in the y is always going to increase because there is nothing subtracting it. This is positive, so this number just always increases in time. So you got to have something negative. If you're curious about why this is so, we can talk about it more. But for now, this is what I have. For the x direction, when you jump, all the speed you have is from your initial jump. So you have some way to break down this vector. The reason I'm talking about it as a vector is because here is the magnitude and here is the direction. And check this out, we have an x and a y. This is exactly why you learn how to decompose a magnitude and a direction into two of the components, because that's where they would fit in. The velocity vector here has to be broken down into its x component and into its y component, and those things go into their respective equations. This is the x that goes here, this is the y that goes there. And I've conveniently labeled it Vx initial, because this is the v in the x direction initially. And then, oh, my bad, actually, I should have put Vy here, no? Vy. In the x direction, we just have constant velocity. There's no acceleration happening in the x direction. There's actually deceleration happening because you're hitting the wind and slowing down, but we're going to neglect air resistance. But when you jump off the ground, you're for sure not accelerating in any direction. You're just coasting at the jump speed that you started with. So this is going to look like Vxi times t, and this is also an equation that we saw before. Oh, by the way, there was one thing here, it was xi, but we saw that xi equals 0 because the guy starts here. So these are the two equations that model the jumper as a projectile. This is what you have to do for almost all projectile problems. Break up their motion into the x direction and into the y direction, and figure out what kind of motion is happening there, and then apply your one-dimensional motion problems. So let's get to breaking apart this vector. I'm going to draw it right here. Here's our vector. Here is the x component. Here is the y component. And the vector has 11 meters per second with an angle of 20 degrees. So let's use so. This is sine of 20 degrees. That equals 11 meters per second over, or sorry, x over 11 meters per second. So this gives me, wait a second. This gives me y, and the same thing for cosine will give me x. And notice 11 meters per second are the only units here, so whatever we get here is going to be in meters per second. I'm going to pull out a calculator real quick and pull out sine of 20. Oh shit. Okay. sine of 20 times 11. This is 3.76 meters per second. And if we replace this with cosine, we get 10.3 meters per second. So check out what we found here. We found out that the guy jumps at an angle of 20 degrees. His original speed in the y direction is actually quite small. He only jumps up a little bit, but his speed in the length is pretty high, which kind of makes sense. He's a long jumper. He wants to jump as long as possible. But you kind of have to optimize between here. We'll talk about what the optimal angle for a long jumper would be in a future video probably, because that's also an interesting question. But anyway, now we have the velocity in the x direction, which we can replace here. So velocity in the x direction is 10.3 meters per second times time. And in the y direction we have 3.76 meters per second times time, plus let's divide 9.8 by 2 and put a minus sign here. 9.8, 4.5, 4.9 meters per second squared, t squared meters per second squared times t squared. So here are the important equations. The jumper's position as a function of time in the x component, and the jumper's position as a function of time is here and here, in the y component. Let's go back to what the problem was talking about. How far does he jump? Oof. Okay. Well, check out how far he jumps. It goes from here, which is a height of 0, goes up, and then the next point it reaches a height of 0. So if the jumper crosses this entire length and then reaches a height of 0 again, I just need to know at what time he reaches this height of 0, and then I can plug it in this extra equation and I will find the length that he has jumped. So how do I find this? Well, let's take the height equation and just plug in 0 here and solve for time. So the height equation looks like this: 3.76 meters per second times time, plus, whoops, it was actually a minus 4.9 meters per second squared times time squared equals 0 meters, right? Because we are looking for the time. Time is the only variable that is in this equation. We're looking for the time when the jumper is at 0 meters. Obviously, if you plug in 0 over here, that is when he is at 0 meters, because he jumps over here at time equals 0 and is starting from the origin. But we need to find another time where this guy's height is at 0. How do we do this? Well, first thing I think about when I see something like this is factor out of a t, because we can do this. Meters per second minus 4.9 meters per second squared times t, right? And then when is this equation equal to 0? There's one scenario when t is equal to 0, this is 0, and whatever is in here, this entire equation will equal 0. Or another scenario where t is equal to some question mark, but whatever that question mark is, it makes this entire thing equal to 0. You see what I'm saying? So if this entire thing in the brackets equals 0, then this equation is true, and that will give us a new time. So when this equation is equal to 0, it looks like this. 0 equals 3.76 meters per second minus 4.9 meters per second squared. And what we can do here is just move the 4.9 meters per second squared t on one side. 4.9 meters per second squared time is equal to 3.76 meters per second. Isolate for time by dividing by 4.9 meters per second squared on both sides. We have 3.76 meters per second divided by 4.9 meters per second squared. Peep the units here. We have meters per second over meters per second squared. If I flip this around and multiply it, I get meters per second times second squared per meters, And here what we have is meters cancels with meters, seconds cancels with one of these seconds. So the only unit left over is seconds, which means this time is going to have units of seconds. So we have 3.76 divided by 4.9. 3.76 divided by 4.9. This gives us 0.76. T equals 0.7. I'll round it to 7.7 because the other number is a 7 after. And this is in units of seconds. So why is this moment in time of interest? It's the moment in time the guy lands. So now that we have that moment in time, we just plug it into the equation that gives us his position as a function of time for the x component right over here. And that is straight up this. I'm going to just take that, copy, paste this right here, and I can do 10.3 meters per second times 0.77 seconds. Check out how the seconds cancel. Second cancels. Meters is the only unit left. This is going to give us the final answer in meters, which is amazing. And we can do 10.3. We can do 10.3 times 0.77. This gives us 7.931 meters, and I'm going to lock that in as the length in the horizontal direction the guy jumped in. But let's check his maximum height. His maximum height. There's two ways you could solve this problem. We found how long it takes for the guy to jump. It's 0.77 seconds. But if you check it out, this trajectory is symmetric. He's going to reach this amount, this height in half the time that it takes him to land, because this length of the journey takes exactly the same amount of time as this length of the journey. So I can just divide 0.77, which is the seconds it takes for him to cross this entire journey, and this divided by 2 is going to give me 0.38 or something like that. 0.38 seconds. Is that true? I'm gonna have to literally check that. And if you have that length in time, then you can just plug that length in time in the y value, and the y value is going to tell you, the y equation is going to tell you exactly at what y value this is happening. And that will give you the answer for part B. So you see how creating these equations for the position as a function of time is super important. It just helps us. You're going to have to do this in all the problems. This is why I just chose this problem to analyze, show you guys what is cool about this chapter. So we have 0.77 seconds divided by 2 equals time at max height. Keep in mind that sometimes you're not going to have symmetric trajectories like this, and you won't just be able to divide the final time in half. But this is a quick leap, and it's going to save you a bit of time. 0.77 divided by 2 is 0.385 seconds. So this is the time it takes for the guy to reach his max height, and this is the equation for the height. So we have this. We're going to do equals 0. We're going to do equals 3.76 meters per second times 0.385 seconds plus. My bad, that's a minus 4.9 meters per second squared times. Here we square it, 0.385 seconds squared. Check it out. This square comes down here. It squares these seconds, which cancels with these seconds squared, leaving the only unit as meters. These second cancel with these second. Only unit left in meters. You subtract these two things in meters, and you will get the final height in units of meters. So what do we get here? We get 3.76 times 0.385. This is 1.4476 meters minus, we have 4.9 times 0.385 times 0.385. This equals 0.726. So the final height is 1.4476 minus 0.726. 0.7216 meters is the height. So here are my two final answers: 7.93 meters in length, 0.72 meters in maximum height. Let's check. The book says 7.94 meters is the range that he jumps, and 0.722 meters is the maximum height. Amazing. That's all I want to show you guys. Here's some tips I have for you guys to study. Make sure you read the book before going to the class, and then when you go to the class, associate the stuff that you hear in the class to the concepts in the book. Do as many of the example problems in the book as possible. Let me know if you want to see a specific problem done on this channel, and just practice the problems. When you're done the problem, ask yourself, what did you learn from this problem? Write that down on a note. Check out this method I have for studying over here. I think it might be kind of cool. And also, keep reading and keep asking questions, and that should be pretty good. I hope you guys enjoyed. I'll see you guys in the next video. Peace out.